This is the third and final coursework, creating our own simple boundary scan infrastructure. After learning about what the boundary scan infrastructure looks like, how it works, and many details, we try to make our own boundary scan infrastructure, although a simpler version than the one covered in lectures and simulated by the Scan-do tool. We will do the following to explain our thought process during this task. The boundary scan infrastructure has 3 in- and outputs, 4 instructions, and uses a free running clock. It implements the mandatory functions as well as the optional override instruction. The clock was designed to be free running to avoid gated clock according to the task specifications. This picture shows the view of the complete boundary scan infrastructure that we were going to make. The final result is the exact same, with the exception of the additional override register needed to implement override instructions. We will explain each component in detail, starting with the boundary scan cell. This block diagram shows the standard boundary scan cell, but with some additional multiplexers and enable signals attached as well. The BSC-CS and the BSC-T are attached to the original multiplexers, and the 2 flip-flops are also part of the original boundary scan cell design. What we mean by the original is how a standard boundary scan cell works, with a capture shift stage and a latch stage using multiple clocks, clock gating, separate signals, or other solutions. Our implementation uses a single free running clock, and therefore we had to add the 2 multiplexers, which chooses if the flip-flops get a new value or keep the old one. This is the code for a single boundary scan cell, which corresponds to the picture shown at the bottom of this slide. The code simply connects the correct inputs to the right places regarding the flip-flops and multiplexers. Something that should be mentioned is the lack of a dedicated flip-flop enable input. But because the flip-flops will always be enabled, we decided to use 1 as a constant input to the flip-flop enable. The 2 multiplexers in the capture shift part have their output signals marked as CS1 and CS2, with CS1 being for the leftmost first multiplexer and CS2 being for the next one. In the latch stage, the signals are marked L and parallel out, respectively. 6 of these cells are connected in the boundary scan register for the 3 inputs and outputs in the boundary scan infrastructure. Because the secondary task was to create an override function for our boundary scan infrastructure, we had to take this into account to make each mode work properly. For example, the transparent signal checks if the BSC-T is 1 and the override signal is 0, meaning that it checks whether or not an override signal forces another output mode to be given. The code shows the port map for the first out of 3 input cells and the 3 output cells that follow. The instruction register cell is a simplified version of the boundary scan cell and contains 3 multiplexers and 2 flip-flops. The first multiplexer alternates between the capture and shift modes, and the other 2 decides when the respective flip-flops are allowed to change value, just like the boundary scan cell. It has a parallel input where the 2 least significant instruction register cells load a fixed binary 0-1 pattern. The purpose of this is to test the tester, since it's important to know that the test infrastructure works properly before it is used to test other parts of a board. The instruction register cell also has a serial input to shift in the instructions and a serial output to shift out the fixed 0-1 pattern. Finally, it has a parallel output to apply the current instruction code to the instruction decoder. The main difference between the boundary scan cell and the instruction register cell is that the parallel input is hardwired to the fixed 0-1 pattern and isn't connected to the parallel output, because the cells don't alternate between transparent and test modes. The instruction register contains 4 cells to hold the 4-bit instructions started initially.
In the VHDL description for the instruction register cell, we have the aforementioned inputs and outputs, as well as 3 inputs for each enable signal to the multiplexers. We also have 5 internal signals between the blocks inside the cell. The first multiplexer selects which input signal to pass on to the next multiplexer, which again selects between this signal and the output from the flip-flop. Next is the flip-flop that takes the internal signal from the multiplexer and passes it on to a new internal signal. The third multiplexer selects between the 2 signals from the flip-flops, and the last flip-flop passes on the output from the multiplexer into an internal signal. Finally, the 2 signals from each flip-flop are sent to the 2 outputs. It's important to note that the flip-flop used for the instruction register will not reset to 0, but instead 1, because the bypass instruction is 1, 1, 1, 1. The bypass register is a simplified version of the instruction register. It is just the capture shift stage made by a MUX and a flip-flop. As the name indicates, this register simply sends the value from TDI to TDO to bypass a group of BSCs, and the whole register is only one cell. According to the IEEE standard, the cell is hardwired to capture 0 when not shifting TDI. The bypass register has, in addition to clock and reset, 2 inputs, TDI and BPCS, and 1 output, TDO. The MUX chooses between TDI and the hardwired 0 with BPCS signal, and the flip-flop works normally, taking in the result of the MUX and sending it to TDO. The instruction decoder uses the instruction from the latch stage in the instruction register to generate control signals. The control signals show what the current instruction is according to the values stated in task specification, which register to use, and if the BSCs should be in transparent mode. We could just use an else statement and drop the else if for bypass, but chose to include both to clarify the distinction between bypass and illegal values. This is a standard test access port controller state machine used in boundary scan infrastructures. It transitions between states according to the test mode select input and generates control signals so we can shift in instructions and data, reset the system, capture logic values, and etc. Here's a list of control signals and the default values. The tap controller chooses which register to output to TDO, when to reset with test logic reset, and it controls capture, shift, and update for all registers. The 2 first states reset the whole system and keep it in idle with default values. The signals for the instruction register is asserted directly in the tap controller. Capture, shift, update, and the correct values to the register selector is generated in the proper states. To be specific, capture IR enables parallel capture and enables updates on the CSFF. Shift IR enables serial shift. FF update sets the register selector, and update IR simply enables the update on the latch FF. Most of the signals for the data register, BP and BSC, cannot be asserted directly, since we need to know which instruction is active. The capture shift signal for the first MUX in the cell, for both BSC and override as they use the same signal, can, however, be generated since nothing is changed on the FFs without the extra muxes we added to avoid gated clocks. The rest is handled on a higher level, which we will come back to, and instead the tap controller sets the register selector and generates signals to show what the current state is, capture DR, shift DR, or update DR.
Most of the top level or main project file is simply port maps for each component we have described. They are all connected using signals. But this is the key part of the VHDL code, where the correct register is connected to TDO and capture shift update signals are generated for override and boundary scan cells. We basically use multiplexers to set the correct value when we are both in the right state and the correct instruction is active. Also note that the capture shift for bypass register is set here because it's used if we shift data while bypass is active. This is a simulation of the first stage of the coursework, the standard operation of the boundary scan infrastructure, with the waveforms provided versus the ones created by our code. The simulation shifts in the xtest instruction, then shifts in all ones to the boundary scan cells, and finally resets. The waveforms are almost identical to one another, showing that our code is working as intended. There's just one key difference when the tap controller enters the test logic reset state. The provided waveforms shows a synchronous reset, with the registers updating on the next clock cycle after reset. We went for an asynchronous solution since it was easier to implement, we didn't have to worry about clock cycles, and it doesn't change the overall function of the boundary scan infrastructure. We will now explain how we implemented the override function, but as we chose a solution with a register, we need to explain where we put it. As the overview shows, it is placed after the instruction register and the instruction decoder, similarly to the bypass register. This isn't really important since everything is simulated virtually, but it helps to visualize the system. The override register is almost exactly the same as the instruction register. There are only 3 key differences. Firstly, it contains 6 cells, the same number as the number of boundary scan cells. Secondly, the flip-flops used for override reset to 0, while the instruction register flip-flops reset to 1, as mentioned earlier. Finally, there is no standardized pattern to hardwire as parallel input, so we just chose them all to be 0, and we could use a generate statement to generate all the cells instead of mapping each cell manually. The key part of the register is the override signal output from the latch stage, which is used to determine the transparency of the boundary scan cells, as explained earlier. In the simulation, we shift in the override instruction, then shift in 0, 1, followed by 4 zeros to override the transparency on the second output. Then we return to bypass, and finally set a couple of different values on the inputs. Again, the waveforms match, and the override function is shown to work in the same manner as the code behind the waveforms provided. The diagrams in the task specification explain the top-level connections and the basic building blocks needed for the boundary scan infrastructure, and because boundary scan is a standardized approach, all solutions will be quite similar. However, the specific implementation of blocks, e.g. having instruction decoder as a separate component versus coding it directly top-level, or asynchronous versus synchronous reset, will vary. This all comes down to personal preference and experience. On the second part concerning the override instruction, we were given more freedom to solve the problem. We solved it by creating an override register. There's bound to be better choices and ways of optimizing the code, but overall we're happy with the results. We hope you enjoyed our last presentation. Thank you for your attention.